If you're listening on the podcast, be sure to jump back to the previous episode to listen to the first half of this conversation. Come back here for part 2.
Welcome to the Building Doctor Show with Jens Johansson.
Okay, now I'm transitioning to stress wave testing. So one thing I want to transition to is some of the non-invasive forms of investigation that we don't do all the time, but we can do, right? It's all about having tools, and when we use them, it's job specific, it's project specific. So one form of testing that we did some research on is called stress wave testing. And stress wave testing basically consists of some instruments, okay? And there is an accelerometer on one end and an accelerometer on the other end. What is an accelerometer? Basically, a signal or a noise or an impact is picked up by one. Think of it as a microphone, but it doesn't project noise. It just records that impact. And then basically that signal is sent across a material, and the second accelerometer picks it up. And then the instrument tells us the time it took for that signal to hit point A to point B. That's it. So these instruments aren't damage detectors. They aren't water detectors. They are simply sending a signal on one end and measuring the time it takes for a sound to move across a material. In this instance, the material, you can probably guess it, is wood, right? It could be plywood. It could be a beam. It could be, we're using wooden substrates. So there's been research done, right? The U.S. Department of Agriculture has documents where they've actually, done testing to certain species of wood, and they've logged those numbers for, Douglas fir, for hem fir, for maple, for every species of wood. So the thought is, can I come out and can I look at a structural member, a wooden member, and without sawing it in half and taking a look at it, without poking it with a stick, without hitting it with a hammer, and beating it, is there a device that I can use to help me determine if this wood is damaged or degraded, or maybe the structural properties have been reduced due to, exposure or what? So we basically rented some equipment and did some lab testing with it. So I want to talk about stress wave testing. So what you're seeing right now looks like a little bit of a lunchbox, and that's basically the device that's going to give me that number, right, that I'm working with. So this zigzag metal device is known as a trombone clamp, okay? And what you can see is there's basically, it's portable. It's a portable device that I can take out. I could set up sawhorses in the field, and I can lay it on a piece of material. So in this instance, you see that there's oriented strand board, right? You're probably used to hearing OSB, but it's a sheet membrane, a structural membrane. We use it like for wall sheathing, for roof sheathing, for floors and whatnot. So the idea is I can lay this trombone clamp on this substrate, use a pendulum hammer, which you'll see, to send that signal through the accelerometer. And then the time it takes for the other side to pick it up is then projected on the lunchbox. Right? So the logic here is, can I record the measurements on a good brand new piece of plywood or substrate? And then what are my readings going to do when I get on something that's more damaged, or, water damage, deteriorated, has insect damage or whatnot? So that's the thought process behind this testing and what this device will do. So, imagine if I took a piece of plywood sheathing off of a building out at one of your properties. Imagine if I sent it to a lab and they told me what the strength property was, that a normal piece of the siding, would have a certain strength value, And then this particular one off the site was, 40% reduction in its strength. Well, now I can use this accelerometer, right, to measure what a piece of siding with a 40% reduction in strength is. And then I can go to other pieces in the field and go, well, do you kind of see where I'm going with that? So that's kind of the logic behind this particular instrument. It's portable. I believe they use these on the factory line when they're actually manufacturing plywood. So as fresh sheets of plywood are coming off of the line, they're basically measuring it and making sure that they're within, what they're constituting a good number, basically. Yep. So now you can see I have a sample that is a water damaged piece of wood. And then what I wanted to try to prove is that based on the orientation of the board, right, there's a strength axis. So a vertical piece of plywood versus a horizontal sheet of plywood is going to have different readings. So yeah, the audio is going to explain exactly what I'm talking about.
You would think with OSB it wouldn't matter on the orientation because all the fibers are oriented in a hodgepodge here, but really I am finding differences when it's oriented parallel to the APA stamp on the back and perpendicular to the APA stamp on the back. You're comparatively testing here. There are ways to calculate properties such as the modulus elasticity of the panel or material that you're testing. But right now I'm just trying to take what I'm calling a good piece of OSB and gather that value and then compare it to other pieces that have moisture damage and organic growth and decay. So establishing my base values, I do have some pieces that I'm calling good, and I do have some evidence of the stamp direction. So parallel to the APA stamp on the back, I'm getting ranges from about 100 to 110. This one, I got a value of 108. In the same sense, when you go perpendicular to the APA stamp, I'm getting readings that are anywhere from about 135 to 145. So those are kind of my values I want to see on a good sheet of plywood. Here's a piece that I found that actually you can see that the orientation of the APA stamp is in this direction. So I would want to see 100 to 110 here, and you can see I got a reading of 135, an elevated time it took to travel across this thing, meaning that it took longer, meaning an elevated level of deterioration or decay. This is a piece that ranges from pretty good on this side all the way to severely decayed or damaged. Unfortunately, I don't have a stamp on the back, and I tried to use these lines to orient it with a good sheet, but really with this factory edge here, no matter which way you orient it, these lines could line up. So I'm actually going to just use the values to kind of try to guess which direction this orientation is going. And you'll see that the numbers are really, really, really elevated in severely deteriorated areas. So I am going to guess that we're actually going parallel with the, perpendicular to the APA stamp. Regardless, a 130, 140 would be normal. I am getting a reading of 150 here, but this probably does have a little bit of deterioration happening. I mean, as much moisture that's been in this board, you know what I mean? I think that 155 is kind of the best side of this piece, and it kind of starts elevating as I work towards a deterioration. So regardless, here's a comparative test. 155 on my good side, 156, 185, we're getting a little spongy, maybe like the threshold of we want to start tearing the sheet off and replacing it with new, and then all the way up to 230. And I can definitely push a probe through this. This is definitely what I would call a failed material. So anyway, that's what I've been able to gather with this material. I'm hoping to do some other types of panels as well, but this is what I have for now. So that is the trombone clamp.
Yeah, so a trombone clamp is going to be used on sheet goods, plywoods, and sheathing, right? There's a different instrument that we use, and it's So basically, stress wave testing, that concept of measuring a signal from one side of an accelerometer to another, that we're timing it, has a couple of different instruments we can use. Yeah, so the trombone clamp is going to be for sheet goods. This is the table clamps. This is another very similar, where you have, you're clamping a device on one side of a panel and you're clamping a device to another side of the panel. There's an accelerometer. There's accelerometer number 2. There's a pendulum hammer. There's a pendulum hammer here. You drop it and it sends that signal across, and then I measure it. Now, a beam, we have a stress wave hammer. Okay, so how do we do beams? Basically, there's the same lunch pail that you're talking about. So I'm just picking up a number, and I have, let's see if there's a picture of it here. Yeah. So basically, we have the hammer in one hand, okay, and then just what looks like a doctor's stethoscope in the other. And they're both connected to leads, right? So you have accelerometer number 1, accelerometer number 2. And the thought is you hold these on one side of the beam or the other, and then you basically record the measurement between. So if you can imagine the time it takes in a good piece of wood, tight grain, no knots, the path of least resistance, right? It's going to be a very low number, a short number, because that signal in a snap made it from one side to the other. As the wood fibers start to break down, as we start to see that water damage, as there's big knots and checks, that signal has to work its way around the resistance to get to the other accelerometer, number 2. So we can correlate those numbers, right, with a quick, good, fast number as quick, good, strong, undamaged lumber, right? As we start seeing that number increase and increase and increase, right, we can start saying, oh man, there's got to be something going on in here. I'm encountering damage or something that's, so it's not telling me I'm a damage finder. This is it. James, you have a hollow post, but I know that the time it's take to travel from one accelerometer to the other is increasing, right? So there have been studies and there is documents. Okay, so the United States Department of Agriculture has a manual that they've created, right? So in this, they've actually done and created the data that helps us with stress wave testing. So they have typical stress wave transmission times, right, for non-decayed Douglas fir at a certain moisture content. So there's information and there's numbers and indicators that we can use, by, USDA and entities like this that allow us to basically take the information that we collect in the field and then apply that to our findings report. So an experiment that I did on a 6x6 pressure treated or preservative treated post, right? Now the cat's out of the bag, right? The post is hollow. We can see that. So like I said, the cat's out of the bag. We know that this thing is hollow, but imagine if this thing was standing 12 feet tall vertically. To the exterior, it looks fine. It looks solid. I hit it with a probe. Wow, this thing's solid. It feels solid. How would I know, other than sawing it in half, if it's in fact this damage like you're seeing here? Well, so that's where I use the stress wave hammer. Now, if you can imagine, okay, what you see right here, this square, as the cross-sectional area of this beam, okay? Imagine green is good, right? And as we get darker and darker toward the brown, right, that's leading to more decay and damage. Now I'm going to ask you, you can see these little points here, 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 here. These are areas where I tapped the hammer and took a measurement, okay? So if you notice, the 4 corners look pretty green and good. Now green for me was a relatively lower number, right? So I was in 900 to 1,000. And you can see on my corners, right? Green is good. Look, we're good here. We're good here. We're good here. We're good here. what happens as I start recording numbers getting closer and closer to the middle of this post? They start getting longer. That resistance is taking a longer time for that signal to get to one end to the other. Oh my God, 3,600. Wow, that got really long. Well, look, I have a complete void here. So that signal hits here, has to go down here, travel, get up here, boom. So that's the concept of stress wave testing. If I can try to visualize it to you guys, is, I can go with a hammer, a stress wave hammer, and tap on a beam or a wood post in the field and not drill into it, not cut into it, not damage it. And I can tell you kind of with numbers, with an electric signal, right, what the cross-sectional area of this post is going to look like if we in fact cut into it. Now, do we do this on every single project at J2? No. But the thought was, can we demo this material, and how would we utilize it if we had to? And this was just a great opportunity to be able to kind of experiment in our lab and show you, the proofs in the pudding. So yeah, it was a lot of input. So here's my table value over here where I had to basically take a measurement, rate the material, and then record, right, and correlate that into an Excel spreadsheet. But I thought it was pretty cool. It's a good diagram to show you that, anyway, I might be a nerd, but I think this was really, really cool. So for what that's worth, that's stress wave testing in a nutshell. Okay, so the trombone clamp, the panel clamp, the stress wave hammer, right, are all the instruments that we use that can kind of measure that signal, and then we correlate that signal with what we would constitute as sound lumber, all the way to there being no lumber there at all, completely hollow, a void, a cavity, So, the device isn't telling me you have a hollow post. The device is telling me that your impact, or the time it's taking from this signal to this signal, is extended, right? So it's up to us to assess these numbers, right, and correlate it to what we're looking at here, which is, a severely damaged post. But yeah, I guess that's the lesson of the day, is that these instruments, these devices, it's the information that you take from them, their output, that you have to put together and analyze and use it in your tool bag, right, to help make a point or reinforce an assumption. So before we break out, some of the different technologies that we use, that are more non-invasive. I mean, really the ultimate one, the most cheap one, right, is what we call sounding, right? I've heard Jens call it the watermelon test, right? Where you're literally knocking using your hand, or using, a blunt object or a hammer, not beating on it, but just tapping and listening for that hollow sound, right? That's a good indicator of, you're going to see damage. So we'll look at a beam, we'll see checking, we'll see some staining coming off of there, and it goes, you know what? And then start tapping on it. And that's a technical term. It's called sounding. And that is what it is. You're basically tapping on it and listening to the sound you hear. And by putting that together, if you've done enough of them, you can kind of feel, you can hear where follow the damage, right? Where it's going to be a fair amount of the time. So like I said, the number one tool, right? Your eyes, your ears, maybe you can smell it and taste it. I don't know. I'm not that good, but sounding, right? That's a good indicator. So then we talked about stress wave testing, pretty technical stuff. We're doing accelerometer here. We're measuring the distance across and, correlating that and graphing it. It's painting a picture. Another method, right, is called resistance drilling. Okay. Now, essentially what the person is doing. So in a sense, the technician has a really cool device that basically fits itself onto your typical cordless drill. Okay. And what they're doing is, the consultant or the engineer is basically going to identify some locations on the beam where they would like this resistance drilling performed, probably in the middle span of the beam. That's usually the area where the most deflection, right, where the loads are the greatest. The beam is working the hardest, so at the top edge of the beam, that would be the compression area of the beam. The bottom edge of the beam, that would be the tension face of the beam. So we have some systematic locations where we want them to perform this resistance drilling, and then that's what they do. And so basically, we see the guys on the ladder, and there's some locations marked out. Here's a point A. You can kind of see a little blip, and basically he's literally just standing there drilling, and a small spade bit is working its way through. And this thing is actually graphing the resistance of that beam real time. And it's charting it on the back of this device. So we're going to look at that right now. And it's really similar to like if you were looking at like a heart rhythm or like a lie detector test, like how that thing is just moving across the paper in real time. And it's just creating this long tab of a graph, right? So as he works through this material, he can then come down and basically, you would think it would be electronic or something like that, but it's a pencil, and it's actually measuring the resistance on a scroll of paper inside of this device. So let's take a closer look, and then you can literally see as he was drilling through, right? And you're working through the thickness. So he went through a 6-inch member, right? And basically notice the big dip or the deviation in the center, right? Which would indicate that the resistance, we're resisting, and then whoosh, there's just this big void. And that's what we're trying to see with the resistance drill if we cut this beam in half, right, we're going to see probably a hollow section in the middle because there's no resistance there. There's nothing to resist that drill as it drills through the wood. So, this device, we use this in a series of locations across the property and utilize some of this data that the instrument gives us to then, put our best foot forward. Hey, maybe we actually really do want to cut into these beams, but we're not randomly just cutting into a beam because we know that then the resistance drill, picked up this big void, right? So in a nutshell, by no means am I an expert on resistance drilling, but that's a conceptual view of some of the other tools that we can use to help us make a more informed decision. Or conclusion, if you will. And so these are samples that we were able to take back. So I mean, the cat's out of the bag, right? But some of the indicators, right, of what might constitute damage, we see some of these lines here, these checks in the beam. We see the staining coming out, the discoloration. Those are all indicators that we would want to, perform some resistance drilling or stress wave testing, or certainly poke and prod at it. Maybe not necessarily cut the thing in half, but if I'm walking through a job site and I see this, that's an indicator to go over and take a closer look. Let's sniff a little bit harder. So, as we, we can jab at it. Look, there's the pen, right? And he's gonna feel it. He might even break out a pocket knife or something like that and just give it a little jab, and it still feels solid. He's sounding, right? There's a sounding, knocking on it. Does it sound hollow? Sometimes it does, sometimes it doesn't. You never know. Wood's different. It's organic. It's got a different grain. Every tree grows differently, right? So there are species, but this isn't a composite material, right? It's organic. We're jabbing at it. It's solid. Look, his probe isn't just sinking in there, So that's where we utilize, these kind of instruments, or, these kind of instruments to basically help us determine, before we just saw the thing off of the chainsaw. So. And then, as we can see, the cat's out of the bag. But, the most economical probe you can use, it's a G2 pen.
Edge perimeter. This is where the pressure treating soaks in. You can see those knife marks, and that's where the chemical soaks into this outer ring. So you have this nice hard shell, if you will, but then you've got just a totally soft.
There it is.
Totally soft inside. It's like a custard-filled donut. That's that end. Then we go around to this side, and you can kind of see the same thing. Oh, you can see the water.
The juice.
Check out the juice. So this is that brown juice coming out that we were first looking at on the edge of the beam. And so again, if I can stick a pen through this thing, that's not a great thing.
So yeah, stick around for live Q&A at the end. We'll answer as many questions as we can in the hour, and then add the rest to the next show. So if you have a more specific question, stay tuned for a link to the schedule. You can schedule a free one-on-one call with me. Brooke's going to be monitoring the chat. I'm going to go through the Q&A panel at the end of the show. So be sure to ask us your questions.
Hey, good job, James. That's a lot of information. I feel like an engineer myself. To going through all the stress wave testing, and the sounding is my favorite. So I actually wanted to start with a story on that, because this happened long before we had stress wave testing and we had the drill resistance testing. About 8 years ago, we were completing a project and I was doing the final walkthrough with the client, and we were focused on signing off, and we had the client and the contractor were wrapping some things up. And the client said, "Man, I'm so glad you guys are about done. This has been a long project. There's been a lot of work. It's been expensive. We're getting all these decks fixed, and just wanted to thank you for a good job. And I'm really glad you're almost done." And I turned to the client and I said, "Until we've gotten off the job site, until we've fixed all the things, you shouldn't say that." So I knocked on a post. I now know I was sounding. And I didn't think I was superstitious, but I might be now. Because I knocked on that post and it made a very unique sound. And I turned to the client and I turned to the contractor and I said, "Will somebody check this for me?" So we didn't have the cool tools out on the middle of this job site. So they just drilled a hole for me. And just like you were showing in the videos, nice piece of pressure treated. This was actually the beam on top of the post. You can see where we did our exploratory. We're going to try and look inside, see if there's something going on. That's what we discovered. I'm really glad we did, because this is one of those crucial elements that support walkways, that support decks. And the rest of it is floating around my office still, because it's been in here for about 8 years, because it's just kind of a really cool tool to show. You can see where the pressure treating goes in, where it's not, and you can see all the way through that. So what's the most practical way for you, James, when you're out on site? Is it to bring the equipment out? Is it to sound? What's the most practical thing for you to do to investigate these posts and beams?
I mean, the cheapest tools we have, right? Our eyes and our ears, and just the knowledge that we've acquired over the years. Starting there, that and just very primitive, probing tools. But yeah, we normally don't show up with, aside from maybe some moisture meters and things like that, just to help. It's really the educated eye, at first, and never doubt. I mean, I say the eye, but then I always have that probe in my hand, and no matter where I'm walking, I'm touching and I'm feeling, because like you said, there are those times where it's like, this thing looks spot on. I'm just going to move on to the next one. And then sure enough, lo and behold, you bury that screwdriver 3 inches into the base of a post, and whoa, document that. So, we do the best we can to be as thorough as we can, but we have a lot of ground to cover. So these visual observations, which is where we start, we use our knowledge, we use our experience, but we're not superhumans, right? So I think it's virtually impossible to see it all, but we see enough to make a good assumption, and I like to think our win ratio is pretty good. So how about you guys? I know everybody has a different style. We're not all the same, but that's, I was in construction for a long time, so I kind of have that eye. I'm always looking at framing things, but I mean, siding, windows, there's little indicators. Everybody has a different style, so it's always nice to shadow our team members to learn little tips and tricks. So yeah.
You showed it a few times in the video. It's seeing that color change in materials. So seeing something like the tannins or the oils from the wood coming to the outside, whether it's a post, a beam, behind some cladding, in a soffit. When you see those colors start to change, there's an organic breakdown that's occurring. And the materials are being displaced. And that's kind of one of those, really should look into this a little bit more and figure out not only what the issue is, but what's the causation. Ultimately, it's the causation. We got to fix that so this doesn't happen again. One of the common things that I saw in the presentation, the video, looking at this piece and these extra posts that are sitting back here behind me, they're all missing the middle. Can you explain from a engineering standpoint, one, the impact of that, missing the core of your wood, but from a waterproofing standpoint, how does that get there?
Yeah. I mean, obviously, missing the core of something, like we depend on that entire cross-sectional area of that member, 100% of it, right, to support the loads that it was intended to support. So when we start decreasing that cross-sectional area, I mean, you can take a big 6x12 beam, right, and it might only have the structural integrity of a 4x4 or 4x8 or 4x6 now. So aside from just the decrease in that cross-sectional area, how does the water get there? Wood is porous, right? Wood is an organic material. So no matter how many chemicals or, the natural tannic acids that are designed, cedar, redwood, these things that have those natural tannic acid that like are weather resistant. There's really no tried and true method. All wood is going to absorb water, whether it's capillary action from sucking it through its end drains like a straw, or just being exposed, right? Sitting there over time with a flat member, looking up at the sky and just getting wet. So yeah, I mean, weatherization, protecting it, shedding the bulk water. Maybe we can't keep all the water out. We can design to let water in, but we're going to let it get out. We're going to design it to be able to not hold on to that water, but to allow it to drain through. So with good weatherization, with good materials, you're never 100% foolproof. But you get pretty darn close. So yeah, I have a feeling we're getting close on time. I don't know. Is there any questions or from other than Jim? Darn it. Love you, Jim.
One of the big things that I've noticed with these posts and beams, though, is when they're brought from a factory, and we'll call it pressure treated, preservative treated, they're treated in some fashion. And we know that the treatment process only goes in so far into a piece of wood. And if you order a 12-foot piece and you need 11 feet, 8 inches, inevitably you have to cut off an area. So now you've got exposed end grains. And so that's what we're seeing with this piece that I shared, and a couple of those pieces that were in your segment. They were probably cut in the field, and those end grains weren't protected. And because of that, water got into that core. And over time, the wood tries to go back to its original state of soil. Hey, well.
So David has a question in the chat. He says, can the infrared camera assist in detecting voids in beams and posts?
So the short answer on that is probably not. The infrared camera senses thermal anomalies, so temperature variations. And it may be kind of tough to see a temperature variation in a post or a beam. Not saying it's impossible, but it's really not designed for that purpose. If you had, for example, a piece of wood that was water saturated, is it a warm day or is it a cold day? And then do you have any sort of temperature changes on the surface of that could affect it? So it doesn't see into things, the thermal camera, but it sees what's being transmitted through things. So if the internal temperature of the wood is super cold because it's wet, it's probably going to transfer to the outside, and we're not going to see that cross section. But certainly, if you sense something, even with the thermal camera, first we probe the exterior of it, and then I knock on it, because we don't oftentimes have all the tools out there. Good question, though. Any others? Okay, well, first off, we want to appreciate everybody for being here today. Make sure that you're all well aware we have a ton of free resources. We think information is key, and sharing that information is very important to what we do. It's information, it's education. As we learn it, we want to share it with other people. So we have a ton of resources for boards and managers. Go to our website, j2consultants.com/resources. You can find a lot of information there. You can catch every one of these podcasts. I know that the regular building doctor, I'm sure, is going to return here shortly. I believe he's going to be on next month with our very own Ken Waldall to talk about landscaping, because Ken is a landscape architect, and April showers will bring those May flowers, so it's a good time to start talking about that. Want to thank you all. Have a great week. Thanks for being here.
Thanks, guys. Appreciate it.
This podcast is part of J2's free live webinar, The Building Doctor Show. To attend the live show and ask your questions during the Q&A, visit www.j2consultants.com.